So welcome to T101 Basic Theory. So here we're going to be looking at a digital binary system. So we have a value, some numeric value, stored in binary within a register file in our digital system. So in the register we're going to call the positive integer that we've got x, as you would with any algebraic problem, and we're going to apply some operation denoted by these inverted commas here to our register file, and we're going to apply this and compare our output to our input. So here the operation that we're looking at is shift the register 3 bits to the left and then add x. And what we're going to look at the output is how many times larger than x is the resulting register value. So what multiplicity value have we times our initial value x by to achieve our output? Here overflow does not occur, and I'm going to explain that on the next slide. Okay, so here we're going to be looking at the arithmetic shift. So as we mentioned on the previous slide, our function is do a 3-bit arithmetic shift and then add the original register. So to look at the arithmetic shift, there's two basic types, the left shift and the right shift. And what we're going to do is we're going to consider a 4-bit number, so 0, 0, 1, 0, the 4-bit number, which is a decimal 2, and consider what a left shift and a right shift does on this number, and also how it works. So we're going to first of all look at the left shift. What we'll do here is we'll just shift the numbers to the left 1 bit. So this 0 is going to move to this 1 position, this 1 is going to move to this 0 position, and this 0 is going to move to this 0 position. And what we do is we bring in a 0 on this end and we reject a 0 on the output. And when we say that there's no overflow, we mean that there are enough digits to incorporate our whole number. So here you can see the maximum we can do without overflow is 2-bit shift. If we did a 3-bit shift, we'd get rid of this 1 and an overflow would have occurred. So let's just do a 1-bit shift on this number here, and we end up with 0, 1, 0, 0. And so as we said, this was a value of 2. So now what we can do is we can calculate what this value is. Well, that's going to be 2 to the power of 2. And that's a 4, so 4. And then if we say we applied a 2-bit shift, so if we moved this 1 to here, this 0 to here, and introduced 2 zeros, we'd end up with 1, 0, 0, 0. And this is 2 to the 3, so that's going to be 8. So what you can see is every time we apply this left shift, we essentially times by 2. 2 to the power of n, n being the number of shifts. And this is just described here, so shifting left by n bits on a signed or unsigned binary number has the effect of multiplying it by 2 to the n. So here we're just timesing it by our 2 to the n. So in our first case we had n is equal to 1, so across here n equals 1, so we times it by 2 to the 1, so 2, and here n equals 2. We've times it by 2 to the 2 across from this original value here. A right shift we can do in the same way, so we start with our 0, 1, 0, 0, 1, 0, we're going to shift it this way 1 bit, so if we do that shift here, we're going to be left with 0, 0, 0, 1, that's a decimal 1. And as you can see, this agrees with the statement down here that shifting by n bits on a 2's complement signed binary number has the effect of dividing it by 2 to the n. Okay, so you can see here we've divided by 2 to the n. So now what we can do is we can start looking at our answer. So our function that we were applying was shift 3 bits to the left and add the original register. So let's start by looking at the 8-bit number with the decimal value stored in it of 1. So that's just a 1 stored in there. Overflow won't occur here when we apply our function because we've used quite a large number of bits. So hopefully our function won't overflow this number of bits. So what we're going to do then is we're going to shift our value firstly by 1. And then we're going to just see the outcome of that. And then what we can do is we can move to 2 and then move to 3. So when we first shift by 1, what we do is we times our original value by 2. As we said in the previous slide, you can see that we've just moved this 1 here. And we can see that's 2 to the 1, which is equal to 2. What we can also do is then apply our next shift, our 2-bit shift. Well, that's moving it from there to there. It's essentially timing this one by 2 and doing a 1-bit shift. But if we go from the original version, it's a 2-bit shift. And we times it by 4. So our output here is going to equal 4. And finally, if we apply the same shift on this but a 3-bit shift or a 1-bit shift on this further value, we're going to end up with this value here. And that's our final value, which is 8. So we can see from the 3-bit shift, we're timesing our original value by 8. And what we can do is on the next slide, just double check that by trying that with a different binary number. So our next binary number we're going to use is just going to be the value of 2. We're going to use an 8-bit number again, so 1, 2, 3, 4, 5, 6, a 1 here, and a 0. So it has the binary value equal to the decimal value of 2. So what we can do is we can apply our shift, as we said we were going to move these bits. All these zeros are kind of going to stay in the same place, so let's do a 3-bit shift on this guy here, and he's going to move to there. So we can then look back to what the output's going to be, 0, 0, 0, 1, 0, 0, 0, 0. Okay, and so what this value should be is 8 times our input. But just to check that, we're going to convert this binary number here to our decimal form. And so that's going to be 2 to the 0, 1, 2, 3, 4, 2 to the 4, which we know is equal to 16. And this confirms that we're also doing a times by 8 multiplication from the 3-bit shift. Okay, so what we now do is apply the final part of the function that we originally had. So what we had to do was add the original number x. So if we add the original number x, the original value was first multiplied by 8, and then we add another x. So we have 8x plus another x, and this becomes 9x. Okay, so we've times our function by 9 finally. So therefore we can see that the correct answer is going to be D. We've times it by 9, but let's just check that by finalizing what we had in the previous slide. And we'll do this on the whiteboard with the original number and the second number we used from the example. So the original 8-bit number we had was the number 1, so it's going to look something like this, and we applied the 3-bit shift, and we ended up with 0, 0, 0, 0, 1, 0, 0, 0. So this was the original number, so let's just label these as x and 8x from the shift, and then what we do is we add these together. So we're going to add these, and the output here is going to be 0, 0, 0, 0, 1, 0, 0, 1. So what we can do is we can just confirm to ourselves what this is going to be in the decimal world. So our original was equal to 1. Then what we've done is we've applied the function, and our output is going to equal 2 to the 0, so 1 plus 2 to the 3, which is going to equal to 9. And so we've got our output is 9 times our input. Let's just double check that then by applying this to the second number that we did, which was 0, 0, 0, 0, 0, 0, 1, 0. So the decimal of 2. And let's apply the shift as we did previously. So this is our 3-bit shift applied to the decimal number. And then what we can do is we can do the addition. So let's label these up again, x and 8x. And then we're going to add these two numbers together. So our final value is going to look something like this, 0, 0, 0, 1, 0, 0, 1, 0. And what we can see is that if we do the addition of these again, so we're going to have 2 to the 1 to convert to decimal plus 2 to the 4. What's that going to equal? That's going to equal 18, which is again 9 times our original value. So we've confirmed that our correct answer is D. So what we can see is that the correct answer is D.